today we're going to look at circular motion, and there'll be a bit of work, a bit of exercise for you to do on that. And to do that, we have to understand that, so here I've got a carousel. So I've got 3 questions for you to start with. Where should you sit on the carousel to get the craziest ride, okay? Is it here, or is it here? So the question is it inside, is it in one of the outer horses, inner horses, or does it make no difference? Okay, do you like the laser effect there? So is it just there, or is it way in here? Alright? All the horses travel round a full circle in the same time. But if you really want to go crazy, of course, I'm sure you know, you'd go in this one. And we'll look at, well, why is that? What's that all about? Okay, so for a crazy ride, you go around this one. That's not a very good pen. Let's try that one. That's a bit better. Okay, now, just a few kind of starting points. We don't really use degree mode. In advanced physics, we use Radian mode. So just to clarify, you know that one full rotation of anything is 360 degrees. Okay? That can be written as 2 pi radians. Now, 2 pi radians equals 2 times 3.14 equals 6.28. Okay? So that's one full rotation is 2. So that's really important to go hold of. That comes up again and again. So one full rotation of a wind turbine. That's ridiculous. Wind turbine. That's a wee carousel or a kid's wind thing. Anyway, you know what I mean. One full rotation all the way around is 2 pi radians, or 6.28 radians. All right. So one quick question then, so one full rotation, so 1 radian equals 360 divided by 6.28, which gives you 57.3 degrees. Okay? You okay with that? Because that comes from 6.28 equals 360 radians equals 360 degrees. Therefore, that's where that comes from, if you're not sure. Okay, over here, right? So let's take this thing here. Now, let's take this point here, right? See that wee dot, okay? Now that dot has got 2 types of velocity. It has a linear velocity, okay? So that would be, it's actually how many meters per second it's travelling. So it's got a linear velocity. But at the same time, as it moves in a circle, so as it goes round and round in circles, like that, it has an angular velocity. And we write that as an omega, not a W, omega. So, angular velocity, and this is in actually, I'm not going to write that. Don't worry too much about the word. Omega is just in the Greek symbol. This is called angular velocity. Angular velocity is measured in radians per second. So if you went 1 rotation per second, that would give you 6.28 radians per second, and that's the abbreviation, by the way. Okay, so angular velocity omega is radians per second, and angular displacement measured in radians is theta measured in radians. So 3 full rotations equals 3 times 6.28, Let me get out the calculator. Equals 18.84 radians. A rad, not rads, just rad. Okay? This is happening there. Now, the most basic equations, some equations for this. So the relationship between theta and omega equals theta over t. And that looks a lot like, I hope you realise this, it looks a lot like V equals S over T, because they're analogous to each other. Okay, so for one full rotation over a period of rotation also equals 2 pi over period. Okay, so we've got so far omega equals theta over t, which is just omega equals v equals d over t, s over t, but in an angular version. And then we say, well, let's make the theta one full rotation. So what's the time to go in one full rotation? It must be the period of that rotation, of a single rotation. And the period of a single rotation is capital T, and the period is how long it takes for the thing to repeat once, okay, to happen once. But obviously you remember, frequency equals 1 over T. So omega equals 2 pi f. So we now have omega, this is for constant angular velocity, omega equals theta over t equals 2 pi over capital T and equals 2 pi f. Now if you've got a wee book going on advanced star physics, I'd sketch those things in there, alright? Now, moving quite quickly here, to take a wee circle. Let's take a circle. Can I draw this okay? We'll see how it goes. Draw a circle, draw a circle. That's an oval. Try that again. That's not bad. Okay, now. Oh, why did that not work so well? So what we've got here is, there's the radius of the circle and S, distance, is the sector length, and this angle here, theta, is there. Now what we find is that theta equals S over R. This is where radians comes from. It's just the size of the sector. Now that obviously works in, that's only in radians, not in degrees. So that's the size of the sector length, and that's the radius. Obviously those are in meters. Right? Okay, it's a really important equation, and because we need that, because we want to have, this is an equation you can be asked for, so write this down somewhere. So there's a derivation of V equals R omega. Now unfortunately, the way to remember this is a mime, because I like to call this as virtual rewind. I'll save it for later on, but anyway, trust me. So I've just shown you that theta, so that's how we can remember this. Hold on, let me put you underline like this. So derivation of V equals R omega, you need that in a minute. So you've got theta, don't let that print just now, theta equals S, so you can write S equals theta R, S for displacement, linear displacement, is VT, theta is omega T times R. obviously the t's can cancel, so you get v equals r omega. And this is how it's usually written. I know how I've done it. Okay, it's v equals r omega. And that's a relationship between linear velocity, and this is quite important actually, it's the relationship linear velocity, like how many meters per second you're travelling, and angular velocity. Okay? Right. Alright. Every linear equation has an angular equivalent. Okay? Let me just clarify a couple of things. So let's put linear here first. So we have, first of all, S equals ut. Now we know the angular version of S is theta, u is omega t. Now I need to clarify a couple of things. That's a constant speed. Right? We also have v equals u plus at. Now if it's accelerating, we deal with these, there's obviously four we need to do about. So v, the way we write this is omega equals omega naught plus alpha t. So alpha, this is the, I have to see that. Alpha is the angular version of acceleration. We also have that we know s equals ut plus a half at squared. So that becomes theta equals omega naught t plus a half alpha t squared. So there's nothing really new there. And then lastly, two more to go, v squared equals u squared plus 2as. See if you can figure that out. Have a think. What would the angular version be? It would be omega squared equals omega naught squared. Obviously omega naught just means initial velocity. Initial angular velocity, plus 2 alpha theta. And s equals u plus v over 2 times t. And that becomes theta equals omega naught plus omega over 2 times t. Okay? And you have to be able to use those. And the experiments I'm going to give you utilise that understanding. So it's really important. Now, by the way, that is not an exhaustive list. There's many more to come, but that will do. That's all you need to know just now. Okay, a couple of quick things. RPM is revs per minute. Okay, so how do you convert that into converting this into radians per second? Let's look at example. 100 RPM equals 100 revs per second equals 100 times 6.28 radians in 60 seconds. Sorry, that's wrong. So let's look at it. Example, 100 RPM. Let's say it was a car was idling at 100 revolutions per minute. That's nothing, but say it was. So 100 revs per minute. Oh, I've done that wrong again. 100 revs equals 100 times 6.28 equals 628 radians. Remember, where does this come from? That is the number of radians in one rotation. Okay? Time equals 60 seconds. So you've got the total distance, the theta, you've got the time, you can say, okay, omega equals theta over t equals 628 over 60 equals 10.4 radians per second. And that's the unit abbreviation of radians per second. There's a couple of questions that involve you changing that over. Now, in the questions I'm going to ask you to do, and you'll see this, there's a few conversions up here, changing degrees to radians. Here's the other way around. Okay, it should be fairly straightforward. This is this RPM thing. I don't want you to do number 4. I don't want you to do number 5. But I do want you to do all these. Okay? Let's look at number 6 just for an example. A disc slowly rotates uniformly at 6. I'm going to give myself a wee bit of space to. I'm going to just give me a second to try and put it down so I can actually write some stuff down and clear myself a little bit of room. Okay, right, it's number 5. Number 6, sorry. It's number 6. This is slowed uniformly at 5 radians per second. So you got alpha, so it's the same as always, write your information. So alpha equals minus 5 radians per second for 4 seconds. T equals 4 seconds. Initial acceleration, that's omega naught, equals 200 rads per second. Calculate the angular displacement at the end of the 4 seconds. So let's see what we've got. We've got alpha, we've got t, we've got omega. We're asked to find omega naught. Okay, omega, sorry. We've got omega naught. So let's see what relates those two together. You've got, remember, alpha equals omega minus omega naught over t, which gives, so that's going to be minus 5 equals omega minus 200 all over 4. So that's going to take that across. That gives me minus 20 equals omega minus 200. So omega is going to equal minus 20 plus 200. Omega equals 180 radians per second. Okay, that's first. What's the angle of this? That's A. What's the angle of displacement? That's A. Let's look at B. What is the angle of displacement at this time? Okay, so we know we've got everything now. We're trying to find theta. So we get all this information. What's the easiest way of doing this? Do alpha equals omega naught t plus a half alpha t squared. So that's going to be 200 times 4 plus 0.5 times minus 5 times 4 squared. 800 plus minus 40, which gives you 760 radians. And that's the answer. So you get the idea. It's just like using the equations of motion. So don't do 5, don't do 4. I've just done 6, so don't do that. Just crack on with the rest. Now these are obviously assuming you know that one day is how many seconds on a day, how many seconds on a year. And they're assuming that you know that a geostationary satellite has a period of 24 hours. Okay? So they'll assume that. Some assumptions they have a look, and that's we've already done that, but you need to know it, so see, just do it. I want to know you can actually do it. So 1, 2, 3, 7, 8, 9, 10. Okay, I'll put it in this, on WhatsApp and in the Teams, and reply to me on Teams if you're not sure. That's done. And just to finish off, I am going to draw a picture of and happily sleeping about. Okay.